Welcome. In this session, we'll explore the solution of a mechanical system that we used in a previous session, and we'll apply the Lagrange dual formulation to this problem. Here, our objective function that has an argument of size 2 is a quadratic form, which is 1/2 times the argument transposed times a symmetric positive definite matrix times the argument, and we have a property function that is, in general, it's some one form, so we'll call it one form number 2, times our argument minus some constant 2. And here, the symmetric positive definite matrix came from the spring constants of that problem, and that was K1, K2 were the diagonal entries, the off-diagonal entries were 0. And in our specific example, we had K1 equals 1, and we had K2 equals 2 in the numerical example from a previous session. Our constraint one form was from the problem, so this came from force balance arguments, and that was minus the first constant times the, and the second constant, and here that will be minus 1, 2, and our external, our constant 2 was the external force that was applied to this system when it was in equilibrium, and we picked the value 6. To solve this, we'll go through our 4-step algorithm. So the first step is to calculate B, which is the constraint one form times the inverse of the symmetric positive matrix times the transpose, and when we go through this calculation, what I find is the scalar 3. It's a good idea for you to calculate that to be sure that I got that right. Step 2, our objective function didn't contain a q-vector constraint, and that means that we can simply write our solution vector as the constraint vector. So in our case, we'll say that the solution scalar is the constraint value, which here will be 6. Step 3 is we take the derivative of the dual with respect to, in general, it will be a vector of Lagrange multipliers, transpose that, and set that equal, in general, to a 0 vector. Here, our Lagrange dual, which is a function only of, in this case, 1, but it could be multiple. So in general, it will be 1/2 of, we take the transpose of the Lagrange multipliers times this B vector, this B matrix, times our multiplier vector, and we subtract S transpose times our multipliers. So when we plug these in, so we differentiate this, so that means that the derivative here will be mu transpose B minus S transpose. We transpose that, and the solution is that B now we'll reduce it to our specific case, which is scalar. There's only one constraint, so there's only one Lagrange multiplier. So B times our optimal Lagrange multiplier has to equal minus S. And that means that our mu star is, if B is 3, then that will be minus B inverse times S, and that will be minus 1/3 times S is 6, and that will equal minus 2. So here, our Lagrange multiplier will be minus 2. Step 4 is, in general, we compute any vector argument is constrained to be minus the inverse of the symmetric positive definite matrix times the transpose of all of our constraints times our Lagrange multipliers. And there's possibly a Q term that we don't involve here. So here, that means that our optimal vector argument is minus, and now when we invert, when we invert a diagonal matrix, that is the diagonal of the inverses. So the inverse of 1 is 1. We leave the off diagonals as 0, and the inverse of 2 is, I'll write that as 0.5. And then we multiply that by the transpose of our 1 form, so that is the vector minus 1, 2, and we multiply that by our optimal Lagrange multiplier. When we work that out, that says that our optimal vector, or minimizer, is, let's take this in 2 pieces. So when I do this matrix multiplication, that is 1 times minus 1 is minus 1, negate that, and that will be 1. This will be minus 0.5 times 2, so that will be minus 1. And the Lagrange multiplier for this problem is minus 2, and that means that our optimal vector is minus 2, 2. Now, let's check the primal problem. The primal problem was we take the K matrix and we put that in, so that will be 1, 0, 0, 2. We write our constraint 1 form, that's minus 1, 2. We transpose it to the vector minus 1, 2. We always put 0 in the lower right corner, and that, when multiplied by our optimal argument and our optimal multiplier, and that had to equal 0, 0, 6 for the problem that we had before. And we can immediately verify that if we take minus 2 times this plus 0 minus 2, that'll be 0, that will be 0, and that will be 6. And once again, our dual solution is faster, it would be more efficient, and it doesn't require solving a matrix that has a mixture of positive eigenvalues and negative eigenvalues.